think I'll make a start. So thank you all for coming. I wasn't sure how many people to expect because usually when I do a talk at this conference, it's my first run of a talk and then I do it a few others. But I've actually done this one 6 times so far, which should mean it's the best one so far, but we'll see. Worst thing about the ACCU conference actually is, apart from the fact there's too many good talks on at the same time, is that it's right in the middle of the hay fever season and you end up not enough sleep and a bit too much alcohol. So apologise for my slightly croaky voice this morning. Hopefully that won't be a problem. Welcome to Functional C++, where I hope we're going to have fun and you'll find it profitable. That's for you to decide. But there is a reason I chose that title. I'm usually a little bit against titles based on memes, but I did have good reason, I thought. And to explain why, I just want to tell you a little bit of a story that's a little bit ironic. I've been doing talks at this conference and others for about 15 years now. And in all that time, until quite recently, the talks that I've given have never been particularly related to my day job. So I've never felt the need to put my company name up before. But, since I've joined JetBrains, that's seemed appropriate. But for this talk, it's the first time all the material here is based on what I was doing in my previous job. So a little bit ironic. And the reason that's relevant to the title is because there's a lot of talks on functional C++. Seems to be becoming quite fashionable these days. Most of them get very academic. They get very caught up in explaining the terminology. And that's great. We need those sort of talks. Nothing against them. But they're not necessarily derived from a real-world application. So I just want to emphasize that this is actually based on real-world use, where we've actually got some quite great value from applying these techniques. Doesn't necessarily mean you will do, but it's certainly worth considering. So, I'm going to get started. And ironically, again, I'm going to start a little bit academic, because I want to, just to establish a baseline, define exactly what functional programming is. Because it may not be exactly whatever your preconceptions are before coming in. So what I've done is I pulled up the Haskell wiki, has a page defining functional programming. I'll just highlight the first line there. Apologise if it's a little small to read, but I'm going to read it anyway. It says, functional programming is a style of programming which models computations as the evaluation of expressions. That's interesting. That's the only relevant bit in that line, that sentence. But a bit further down the page, it goes on, say, in functional programming, programs are executed, again, by evaluating expressions. In contrast with imperative programming, where programs are composed of statements, which can change global state when executed. Functional programming typically avoids using mutable state. Simple paragraph. There's actually a lot to unpack there. And in fact, we're going to spend most of the rest of the talk discussing the implications of this, and only even then scratch the surface. I think it's a sign of something quite profound when you have something really simple that has those sort of consequences, makes you think. But just to pick this apart now, the important part was that contrast between evaluating expressions versus statements. So we know that C++ has statements, has if statements, switch statements, for and while loops, has lots of statements. So I think we can say that C++ is not a pure functional language. I'm sure that's not a surprise to anyone. That doesn't mean that we can sort of coerce it, or we can't coerce it into using a functional style. We'll come on to that in a moment. But what about the evaluating expressions? What does that actually mean? You may have in mind sort of mathematical expressions, and it's certainly true that functional programming does have a lineage back to mathematics, and that's one of the problems with that academic coverage is that it gets caught up in the mathematical terminology, which is maybe not familiar to us. Doesn't mean it's not simple, doesn't mean it's not very valuable, but I'm going to generally avoid discussing much of that in this talk. But we will have a look at what it means to evaluate expressions as opposed to statements. And then this is interesting. Talking to statements, it then relates that to changing global state. You may not have really sort of seen the link between those two things before. but there is a direct link, which I'm going to come on to just next. And then finally, it says the functional programming typically avoids using mutable state. Doesn't mean it always avoids it. And in fact, if it did, it wouldn't actually be that useful, because we need mutable state in order to get things done. Mutable state and side effects are often used interchangeably. They're not completely interchangeable, but to a first approximation, that's the case. So I might switch between those two terms. But let's get back to the expressions and statements. So this first section I've called expression-oriented programming, which I think might be like a useful reframing of what functional programming is to get us away from some of the things we might have been thinking about. And let's start with a simple piece of C++, some typical code that you may have seen or written hundreds of times. This is obviously not functional. We'll get onto that. But I just want to pick apart the problems here. You can probably see a few problems already, but we're going to discuss it in the context of what we've just been talking about with expressions versus statements. So what are the problems? Well, what's the intention of this code? Well, the intention is that we want some variable, color here, to get this value that's conditional on some other call. Now, I use the word get there just to try and get away from mentioning that this is an assignment here. The intention is not to use an assignment. In fact, it would be preferable if we could use initialization, but we want it to end up with that value. The reason we're using an assignment, which implies mutability, is because we're using an if statement here. If you think about it, the only way to get the value out of the scope of this if statement is through that side effect of immutable assignment. It's not strictly true. There's actually one other way, which we'll come on to in a moment. But that's why we're having to do it here, because what we really want to do is initialize our variable at the top. And as a result of that, there's a few other problems here. After this code, we may never need to change color again. It's very likely that's the case. So it'd be nice if we could make it const, but we can't because we need the mutability in order to give it that initial value. Also, we don't have an initial value. It's an uninitialized variable up here, and a lot of people don't like that. Maybe you've got a style guide that forbids it, or you're running some lint tool that's going to complain about it. So we might give it a default value, but that's not really what we want. Again, it's not part of the intention of what we're trying to write. What value are you going to give it? Some sort of sentinel value maybe, or maybe sort of this value, and then we drop the else clause. It just doesn't, it's not really expressing our intention very clearly, and we're having to work around it a bit, and we've still got the mutability problem. So it's quite a lot of problems in such a small, simple piece of code. You may not think they're big problems. Actually, the biggest problem is the mutability. If we've got lots of code after this, then as we're reading through it, we have to consider that color could potentially change at any time. In order to verify that it doesn't, we've got to examine all of the code that it runs through. And if all of your code base is like this, you've got to consider your entire code base every time you want to reason about anything in it. Now, we don't do that. That doesn't mean the problem doesn't exist. We just got used to the fact that we can't cope with that. We sort of consider it just the cost of doing business. We deal with it by debugging after the fact, but we don't have to. If we made all of our variables immutable, where they could be, then there's whole classes of problems and issues that we don't even have to think about because they're not allowed. It's something called local reasoning, where we can reason about the value of something simply by its well, in this case, the initialization of it. We don't have to consider the rest of the code base to reason about that. And that's something that you hear functional programmers talking about, being able to reason about the code. And that's one of the ways that you can do that. Make code something you can reason about by avoiding all the complexities of all the interactions between mutable variables and side effects. So what can we do about this? Well, let's hypothetically, just for a moment, imagine that C++ was an expression-oriented language. And rather than if being a statement, it was actually an expression. What would that look like? It might look something like this. So we've still got the if, but now it's an expression. Rather than having to do something in each branch, we just evaluate to a value. In this case, the constant that we want. So now the whole if expression evaluates to a value. And because of that, we can assign it to our variable at the top. So we don't have an initialized variable. We don't have the assignment. We can make color const. And as a bonus, we didn't even think about this, we can now use type inference as well. So that's nice. In fact, that is actually really nice. It's a shame we can't do this in C++. And if you look at other functional programming languages, one of my favorites is F#. This is how you do it there. Apart from some minor syntactic differences, that's exactly the same. This is how you write normal code in F#. And when you've been doing this for a while, you get used to it. You can't imagine doing it any other way. You go back to C++ and the code I showed you just now, and it seems barbaric. How can you work like that? There's really no downside to this. But, of course, we can't write code like this in C++. And you're probably sort of bursting to tell me that, yes, you can. You could use a ternary operator, of course, yeah. That works. That actually gives you all of the same advantages we just discussed. I know a lot of people don't like using the ternary operator, and they cite maintainability and readability issues. And yeah, there's some truth in that. You do have to be careful of operator precedence, and if you nest things, that gets very messy and unreadable quickly. But if you're careful, if you keep it simple, make sure you use brackets judiciously. This is fine, actually. I use this sort of style quite a lot. It's quite a nice way to do it. You do have to adopt to like a consistent formatting to make that readable, but yeah, the real problem with this is it's just not general enough. I mean, it's fine for this particular case, but what if you've got, say, more than 2 cases? There's another example. Now we've got to resort to a switch statement again. You can't do this with a ternary operator, not without lots of nesting, which we just ruled out. So we've got all the original problems back again, for all the same reasons. Not going to go through them again. Now, how can we deal with this one? We don't have some built-in special case to help us. Remember I said earlier, there was one other way to get a value out from within a statement. And ironically, is to use another statement, the return statement. So what we're doing here is we're pushing the switch into a lambda expression and returning out of it. And down here, you see, we're immediately invoking the lambda. So we're not storing it anywhere. And that actually gives us all those same advantages back. Everything we discussed before, but now it's general. So we've got our constant, we've got the no uninitialized variable, no immutability, type inference, it's all there. But isn't it a bit of a heavyweight solution, bringing a lambda in? Well, first of all, this is less code. I think there was, I forgot, but I did count it. I think there's something like 13 less characters in this. It's mostly because of the breaks in the original example. But I mean, it shouldn't really matter, but don't let that put you off. Less typing for this. Okay, what about performance? Surely introducing a lambda, we've got function call overhead, we're returning values. Got to be a performance hit. Well, you'd expect any decent compiler to optimize that away. It's not just an expectation. I did check Visual C++ and GCC, check the disassembly output, and the only difference was with GCC, I think, you get 2 copies of the lambda in assembler, the inline and the non-inline version, and I would expect the linker to strip one of those out. So essentially, identical code. In fact, it may be better than that. This may be more performant. So in this particular case, where it's just an enum, yeah, it would be the same. But what if state was actually a more expensive to construct type? The original example, with the uninitialized version, you've got a default construction of your type, and then later you've got an assignment which may be more expensive. So here, where you avoid that, and where you've got return value optimization and or move semantics, we can actually avoid some of that expense as well. So potentially this will perform better than the imperative version. So all those things that make this sort of code easier to reason about for us makes it easier to reason about for the compiler as well. If the compiler can see more opportunities to optimize, you can get more performant code. That's an interesting thought because functional programming is often seen as because it's a higher level thing, reduce the scope for optimization, but that can be the case sometimes. This can also be the case as well. Okay. Before I move off the statements, I mentioned that loops were also statements, and that's true. So for all the same reasons, we create a scope that we need to get values out of. How do we do that? Basically the same, except really we don't really want to be writing raw loops if we can avoid it. I wouldn't use standard for each either, because it doesn't buy you much in this particular case, but what we want to reach for the more specific algorithms. Got standard transform and accumulate here. These are all examples of what we call higher order functions. And all that means is that they are functions which take other functions or function-like entities, anything that's callable, or returns a function or function-like entity. So these will take, well, these days it would be lambdas, it could be function pointers, and so on. Here's, I think, the complete set in the standard library. Most of them are just these sort of if forms. We can pretty much ignore those. These are the important ones at the top. The reason I've highlighted those is because they map onto these names you may recognize from the functional world: map, filter, and reduce. You could argue whether accumulate is the same as reduce. Technically, it's more of a left fold. It's approximately the same sort of thing. So this is really useful, but unfortunately, there are some limits to the way standard algorithms work, which make them not quite suitable for what we might think of as functional programming. And I'm going to come back to what that limitation is and how we can get around it a bit later. But I just wanted to talk about loops and how we can replace them for the moment. Now, I'm going to take a slightly different tack now and talk about something called the builder pattern. And this is continuing this thread of how can we make our data immutable. We sort of touched on why we want to do that, because it helps us to reason about our code and avoid unnecessary complexity. But that decision in itself introduces some other challenges. So the builder pattern, well, I call it that. I've heard other people call it that, but I think some people use different names. I'm not sure if there's a universally accepted name for this, but the point is it's actually something really simple. It's so simple that you might think, well, why does it need a name? But like a lot of these things, you can easily miss the nuance to it. So I'm going to try and labour this point a little bit because it's going to be foundational and we're going to build on it as we go forward. So we said we want to make things const. Obviously, const and immutability are not exactly the same thing. And there's a few problems with const in C++ in this regard. One is that it's not the default. So we have to sprinkle const everywhere in our code. It gets a bit ugly. C++, we have to deal with it. Another problem is that const is not transitive. So as well as on the top level, like here we've got these pointers, we're going to make the thing pointed to const as well. And then so on and so on. So this person class, that needs to be an immutable class as well with const members and so on and so on. We can only do that by convention. Compiler's not going to help us much with that, but that's where we are. But we can do it. We've been doing C++, we've dealt with this sort of thing before. That's fine. Now you notice here I've also deleted the default constructor. The reason for that is because our data is all immutable now, we have to construct it in a fully valid form. We can't change it after the fact. So default constructor is usually not useful. And in this case, we won't get one anyway because of the constant and the const ball. But I like to make it explicit that I know what I'm doing and this is what I intend. There's no default constructor here. But apart from that, there's no mention of any methods in here. And if you think about it for a moment, a lot of methods are to do with mutability or accessing the variables. And in fact, a lot of what we use encapsulation for is to manage, encapsulating what happens when you change state. Well, if you can't change a state, then you don't need to encapsulate that. So very often, not always, very often, just make all of these data members public on these sort of data types. This is like a typical domain type. Very often, they can just be simple structs, all public, all const, no or very few additional members. And that makes this nice and clean and uncluttered. And again, this is an often overlooked fact when you try to apply functional techniques. Often we concentrate on, well, I've got to do all this extra stuff now. Or this is more noisy, like with all the const. But actually, you're getting rid of a load of stuff as well. There's no getters and setters. I don't even have any additional constructors here. So how do you construct one of these? Well, because it is just a set of public data members. Is that going to work? The battery's run out. You can use MemberWise initialization. I think that's actually a great use of it. So we don't need an additional constructor cluttering that up. You can have one if that's appropriate. None of this is prescriptivist, but I found this really useful. Because now the public layout of this class is part of its contract with you, so I think it's fine to rely on that. And this is good. We're constructing it all in one go, so we don't need to rely on any mutability. But there is a small problem. Well, we've got to get these additional objects from somewhere, and with typical domain types. By the way, obviously this is a contrived example, just made up for purpose of this talk, but it's sort of based on the sort of objects I was working with in my previous role, which was on a quant library at a bank. So lots of financial objects with dependencies between them, big object graphs. So think of that sort of code base in these examples. So we've got dependencies on these objects. We've got to get them from somewhere. And again, because they're immutable, you've got to go through the similar process where you've got to construct them all in one go. So how do we do that? Well, unfortunately, that starts to get very messy in our code. Again, try to approximate the sort of code that you might see. So at the top, we're getting this person object. And then to get an address from that person, we need to use person to call some other object. And there's all these dependencies, not just between the objects themselves, but just in getting the objects. It does get very messy. I'll make this even more complicated in a moment. But what I want to draw your attention to here is now, because we're making employee purely immutable, we've had to effectively replicate the structure of that type in these local variables. We've got all the same types again up here, plus a bit more. So that's sort of creeping in the direction of we're adding lots of extra code. Don't want to do that. If it was mutable in the first place, I could just default construct it and then sort of gradually populate it as I get these values in. We can't do that here. So can we have our cake and eat it? Almost. Right, so what we do is, having observed that we've replicated the structure up here, let's formalize that a bit more. Rather than just local variables, let's put that in its own struct. I call that employee builder. It's where the builder part of the builder pattern comes in. So the sole purpose of this class now is to act as part of the construction of our immutable object. That's why I call it a builder object. So note, these are all now mutable members. Now, only at the top level, they're still pointing to immutable types. It's only the level that we're building up that needs to be mutable now. And you might think, well, that's a bit wasteful. I'm duplicating my types now. Well, we sort of had to do that anyway, but now we've only got to do this once. We have some other opportunities. So I've added this build method here. It doesn't have to be in here. It's just a nice convenience. This sort of says, well, this is the way that we now, once we've got this data, we actually build our immutable type. And you can add extra things on there, like you can put some validation in here, so you don't have to put a constructor on your immutable type. You can enforce the fact that it's always created on the heap and returned by shared pointer. That can be useful. These are all things you can do with it that are not strictly part of the pattern, but it's a nice thing you can do. So looking back at the calling code now, looks a little bit simpler. So we create our builder at the top. We can progressively populate it as we get data coming in. And then when we've got everything, we say .build. Simple. Still a little bit more code, but it's manageable. So what's the benefit of this? Well, the benefit is that the rest of the code base, we can work with our purely immutable data. And the benefits that we can get from that with local reasoning, and some other benefits to do with concurrency and other things we'll talk about a bit later. But we haven't had to give up all of the conveniences of mutability. What we have done with that is we've really restricted and managed its scope. We're explicitly distinguishing between this builder phase here, this construction phase, and the built phase. And I can't remember where I first heard it or which language it was in, but there is a language where it has the terms raw and cooked in constructors. It has exactly the same sort of thing. You're immutable up to this point, and when you're done, you're cooked, and from that point on, everything is immutable. That's a nice way of doing it. So this idea of separating the construction phase and the usage phase is really useful for getting the most out of immutable data. And as I say, that's a foundational thing we're going to build on through the rest of this talk. So maybe I haven't convinced you on this particular point. It's a little bit difficult to go into all the ins and outs just in a few slides. You just have to try it for yourself. I found it really useful on a large code base. Just a little bit more on it. Let's imagine that looking up the address for the person involves an asynchronous call. So just highlight that. So you can see we've got this contacts book here. We call a wait on it. Obviously, coroutines can potentially change all this, but we might work with code like this. Pass the person class in, and a lambda. And the lambda gets called back when the data is retrieved from the database or wherever we're getting that from. There's a few interesting things about this lambda. See, we're using C++14's generalized lambda capture. That allows us to move our partially constructed builder in, so it should be fairly efficient to do that. And then we can continue building it through the rest of the lambda until we're done and we can build our employee object. Obviously, I've left it ambiguous what we're going to do with it after that. We do have to make the lambda mutable as well to do that. Again, C++ syntax, it's very noisy. Other languages, it's much simpler, but we have what we have. But that's actually quite nice. If we were back with having individual variables in order to be able to construct our object, then let's say we'd initialized about a dozen of them before this point, and then we had some more in here, we would have to individually move each of those dozen variables into our lambda before we could continue. We could do it all in one go here. So again, that's quite nice. Nice little extra thing we can do. All right, I'm going to come back to that sort of thing in a while, but I'm going to take another little slight detour and talk about strings. And you may wonder what this has to do with functional programming. The promise is a fast and safe ref-counted string. Now, if you've been around C++ for a while, you probably remember that standard string originally, it's designed, it wasn't designed to be reference counted, but it was designed that it could be reference counted, and some claim that that wasn't actually achieved. But nonetheless, most of the original implementations were internally reference counted, which is great, less copies of strings. But there's a problem. Standard string has a mutable interface, and mutability and reference counting don't really mix very well. So we employed this technique you're probably all familiar with called copyonwrite, or cow for short, which makes for an interesting visual. We all loved cow, didn't we? So I'm sure you're familiar with it, but because I'm going to build on this, I'm just going to whiz through what it actually means anyway. So here's what we want. We want our copies of our strings to share the same underlying representation. So we've got a pointer to some buffer, contains the characters, and then a reference count. So we've got 3 strings here, pointing to a buffer, reference count of 3. That's simple, that's nice, that's what we want. But then the problem comes when we need to mutate one of them. So this third one here, having been shared, we now want to remove the character. So at that point, we make that mutable operation. We need to say, if we are shared, ref counts more than 1, take a copy and mutate that, or take a mutated copy, whichever way you look at it. Okay, well, I mean, that worked, so it seemed. So that's what we did. But then we discovered problems with this. 2 problems, actually. One was performance. In fact, what we found was that cow runs like a dog. And the main reason for this is because there's lots of extra checks to the reference count, because a lot of this mutable interface, well, even if we're not actually mutating the string, we may accidentally call the mutable part of the interface, and we do that check unnecessarily, maybe make unnecessary copies. And to begin with, the reference counting itself wasn't very efficient, because to be thread safe, we had to either lock it or use atomics, which weren't as good as they are now. And, well, if you were there at the time, you know the story. There was another problem, though, as well, which was to do with correctness. Because if you had references or iterators into a string that was shared, and then one of the shared ones changed and it became deshared, you might actually end up with a dangling pointer because of something that some other code did, which is not a very good situation. In fact, that was allowed by the 98 standard and was fixed in C++11, but fixed in such a way that you can no longer write a copy and write string that makes sense. So that was the main reason that I believe that GCC eventually moved away from it. So now most, if not all, string optimizations, string implementations use the small string optimization. So that's where we are today with standard string. But remember we said that the problem was because standard string had this mutable interface. How does this all work if we actually have immutable strings? Well, let's go through the scenario again. We've got our shared strings pointing to an underlying buffer, reference count of 3, and that's it. End of story. There's no mutable stage to worry about. That's where all the problems were. Well, we still have to work with reference counts, but actually now we've got lots of other ways to deal with that as well, particularly move semantics. Means that a lot of the time we don't even have to consult it. So again, in my previous role, I had exactly this type of immutable string implementation, and at one point I was in a position to take some benchmarks. Don't have the figures now, they were part of my role before. But with a large sort of real-world test case with thousands or millions of these strings floating around in memory, I tried 2 alternate implementations. One that was more like standard string with a small string optimization, and one that was like this. And this version was significantly better performing. As well as all the other benefits we've already talked about with immutable data. So what's the problem with this? Well, problem is there's a reason that standard string has a mutable interface, and that's that sometimes we do actually want to mutate them. So how can we allow for this as well? Well, to some extent, this is handled by, well, I've called them string refs here. C++17, we get stringview, which allows us to take non-owning references into existing strings or substrings. And this handles a lot of cases where we may have needed mutability, at least some of them, but they're really useful for other reasons as well. I'll come back to that. But most of the cases are handled by the builder pattern. So just like we discussed before, you had this companion type. I called it stringbuilder. And stringbuilder is now optimized for mutability. So you can do all the mutable operations. You probably can't see the words there, but you can see the graphics. So we can mutate strings in place. We can change the size, truncating or reallocating them. Now it does have a reference count, but it's always 1. In fact, within stringbuilder, this doesn't even need to be atomic because that never changes. Now the reason that we have that reference count there at all is because once you've got the string in the shape that you want, then you don't need the string builder anymore, you need a string. So you can detach or move the underlying representation with the reference count into an immutable string. And now you've got that sort of transition in ownership. It's in one place. I've used the word detach there because my implementation was before C++11, before we had move semantics. These days, it definitely would be a move with our values. Either way, it works the same. So now, the immutable interface here no longer has access to this string, so that's safe. And the immutable one can't change it, so it's safe. So we can freely share that string as before with other strings, just increment the reference count. And then later, if we decide, actually, I've got this immutable string, I want to change it, well, we can construct a string builder from that. And if it's shared, we'll take a copy. Sounds very familiar from the copy and write, except now it's explicit. There's no way you can get this wrong because you have to explicitly say, I want to copy this into a string builder now, and it will check the reference count and do the copy. But that's the only time that happens. But if that string happens to be not shared, single reference count, and you do a move on it, we can actually move the representation back into a string builder where we can safely mutate it with knowing that no one else is going to touch it. and then move it back again. So we've got pretty much 0 overhead compared to not having the 2 types. But we're managing the lifetimes of the mutability. Just to put that visually, just to be absolutely clear. So, our string builders here, we safely transition into this immutable usage stage. Later, we may transition back into a string builder, and then back again, and so on. It's very safe. It's fast compared to copy and write. As I said, in my benchmarks, it's faster than standard string as well for our usage. Maybe not everyone's. And it's reference counted. So that's strings. You could consider strings, I don't know if you can see that actually, it's not very bright. It's just a series of boxes meant to represent an array. Strings are a special case of arrays. So everything we just discussed with strings, you could apply to arrays. And in fact, we did. We had immutable arrays, array builders, array views, or array refs. And they were useful, but not as useful, because usage characteristics of arrays tend to be a bit different. Lots of mutation in place, very expensive to copy large arrays, and so on. There are ways to mitigate that. You can have things like ropes, where you have non-contiguous arrays, so you take bits of it. We didn't do that. We just mostly use standard vector most of the time. That was fine for our usage, but there are approaches there. Where it gets more interesting is in slightly different data structures, mostly associative data structures. And this is where we can borrow another technique from functional programming called persistent data structures. I'm going to explain what they are. But just first of all, to be clear, the word persistent here doesn't refer to the file system or a database. It's about when you have an existing data structure and you want to change it, you take a copy, but the original version persists. It sticks around for as long as you need it. That's where the persistence comes in. But the trick in this technique is in making that efficient. So when you take a copy, you actually share all of the common state, or as much of it as you can. And that's what these techniques are about. So to illustrate that in the simplest form is with a singly linked list. So sure you know how singly linked list is implemented, but again, just to recap, in the context of persistent data structures now. So each element in the list has a value and a pointer to the next element, or the previous, depending on which way you look at it. We typically call the first element the head, and then the rest is the tail, so the pointer to the tail. And it's important that it's a singularly linked list with pointers only one way. And the reason that's important in this context is because actually you'll have some list object which itself has a pointer to its head. And if you take a copy of that and add an item, say, then you can end up with a second list which has a pointer to the new head, and that head has a pointer to the head of the previous list. What's significant is that this list knows nothing about this one, but they're sharing all of the common state. So it's, from that perspective, this is really efficient. Unfortunately, lists themselves aren't particularly efficient in C++. We'll come on to that, but you can do it the other way as well. If you remove an item, well, now you have a new head with a pointer to an earlier node. You can keep on doing these as much as you like. Now, in this case, you can see all of the different generations of this list, hold them in memory, efficiently sharing state. But if you don't need these, if you think of them as just reference counted, drop those. You've only got the memory that you actually need. That's nice. As long as all of the operations you're performing are at the head. If you start working down here and mutating here, or especially right down the end, then it becomes much less efficient. You end up copying everything all the time. So it's not so useful in C++. So the bread and butter data type of functional programming languages. And it's surprising how often you can change the way you're doing things to keep operating at the head. The bigger problem in C++ is that because of all the pointers and dereferencing, it's not particularly cache-friendly, not very efficient for our needs. And I said before, we don't want to give up performance to get these. So I don't recommend using this, but that's just to illustrate what we're talking about. So let's have a look at trees. On the face of it, actually not that much more to it than the list. we have a number of elements, each with a value, but now 2 pointers, with a left and a right pointer. And this relies on us being able to order our values, and that's why it's an associative array, or associative data structure. And the idea being that at each point you can do a binary chop on the values and find your position in the tree. So if you introduce a new value, then you can walk down the tree to see where that's going to slot in. And important to note that actually you can associate it with either the left node or the right node in this slot. That's useful to have. In this case, we're going to put it down there. Now, when you put it down here, now you've got to write a pointer into the parent node. And if this is just a standard binary tree, that's it, you're done. But if we want to make this immutable and persistent, that's a problem, because we can't mutate the node that's already there. So we're going to have to take a copy and write the new pointer into that. So we can do that, but now we've got a new node here. We need to do the same thing to its parent, and so on, all the way up to the root. That's typically what happens. We rewrite all the nodes up to the root. We now have a new root, but here's the thing. We still have the original tree in its entirety, exactly as it was before, doesn't know anything about the new root. The new root is sharing a lot of the common state, not as much as in the list case. Typically, it's sort of about a 5 to 10% overhead for any sort of trees of a reasonable size. So that works, you can do that. This is a simple binary tree. The limitation of this is that you can get very different depths of the tree. So you might get some very shallow branches and some very, very deep branches. And it's really easy to get into the pathological case where you just have effectively a linked list you've got to walk all the way down. So we'll come up with techniques for rebalancing the trees. The standard set and map tend to use the red-black tree. I'm not going to go into exactly how that works, other than that you hypothetically color each node red or black. Depending on which color it is, you have different rules about what its children can be. And if you apply those rules and sort of rip all the way up, it rebalances the trees to be approximately the same depth within 2 or 3. And how does that affect making this persistent? In short, it doesn't. There are some implications in that as you go up, doing the rebalancing while keeping things immutable gets a little bit more tricky, but it's doable. And because you are rebalancing and shuffling nodes around, you tend to get a bit more copying involved. So there are optimizations that you can apply. Again, if you consider that each of these pointers are something like shared pointers, as you're walking down the tree to find the place you want to put it in, you can see the first pointer which a node is shared. At that point, everything under it is considered shared. And then you can say, well, if it's not shared, then I can actually mutate in place, because that means the root is not shared, no one else can see it yet, so we're probably on this new branch. So we're still in that raw state. So until it's cooked, we can still mutate it. That's quite a nice optimization. So again, we found for mutable operations on these persistent red-black trees, we had something like a 10% performance overhead on insertions and deletions and so on, which was great considering what this gave us. Particularly, probably the most important thing for us was the implications for concurrency. If you share the root node somewhere, shared between threads, and you have something writing to it, then you build up your new tree, and then you can do a single atomic swap operation to write that in to the shared location. There's a little bit more to it than that, and you often end up having to go into a compare and swap cycle. But if there's not heavy contention on that, then it's typically much more performant and much easier to reason about than using locks. But it's not just concurrency as well. So we were working with financial objects, and one thing you often want to do is build up this big object graph and then speculatively change some of the variables involved to get new values for some of the objects and build up this matrix of all the possible values called a scenario. And what we had to do before was go to each point individually and roll back, because you couldn't hold all these objects in memory, it's too much of them. But with all the sharing of these nodes, with a persistent data structure, we could keep everything in memory and just move around freely. It was really nice. Solved a lot of problems. So we've got performance, we've got easier to reason about, and we've got other benefits from doing this. And that actually turned out to be good enough for us. But in general, these sort of tree structures are not the most performant these days. So we know that now we have standard unordered map, unordered set, particularly for large collections, are much more performant, much more cache friendly. And the problem with these trees is they can get very deep. So if you have, say, 16 million objects in there, just pull a figure out the hat, you'll typically get a tree height of around 24 nodes deep. So that's a lot of pointer hops to get to any particular value. A lot of cache misses you'll probably get. And the reason they get so deep is because you've only got the 2 pointers in there. If you've only got 2 pointers, you're limited on how shallow you can keep it. So the solution, of course, is to put more pointers in each node. Don't know where that came from. The more pointers you can put across, the shallower the tree. Simple. But how do you do this? So there's a couple of problems here. One is that by increasing the number of pointers you keep in each node, and assuming that most of these pointers are going to be null most of the time, they're not always going to be full, that's not going to be a very efficient representation in memory. Most of it's going to be wasted. So what we do there is we use a technique of bit mapping the array. So say you have a logical array of 32 pointers, you've only got, say, 6 of them actually full. Well, you store a physical array of 6 pointers, and then a word where each bit, I've got the graphic, each bit represents which pointer is actually set. So these first two are set, so they are the actual positions. The third one's not set, so that's not in there. The fourth one is set, so the third item in the physical array is the fourth item in the logical array, and so on. Reasonably simple. Actually doing the mapping is a little bit more complex. There's some really interesting bit twiddling techniques you can use to make this fairly efficient. There's even a single processor instruction on some architectures to do it. Won't get into the details, but it's a nice solution to that particular problem. And what you end up with is each node is either a value on a leaf, or if it's a branch, then it has one of these compact arrays in a bitmap. But how do you know which pointer to follow? With the binary tree, it's simple. It's just, greater or less than, left or right. What do we do here? Well, what we do is we actually hash the value, and we divide the hash up into chunks of 5 or 6 bits. And that becomes the index into the array as you walk down. So I've only drawn 4 bits in here, just keep it simple, but start at the top. So if this is our hash, you can see the first 4 bits here, second 4 bits, third 4 bits, and so on, until you get to a leaf. And same as with hash maps, the leaf actually may contain more than one value because you may have to do a final linear search, so think of it more as a bucket. So you've got some of the properties of hash maps and some of the properties of binary trees. Turns out this is actually closer in performance characteristics and other characteristics to a hash map. And in fact, I have a proof of concept implementation that performs almost identically to a standard unordered set. Technically, you do still have a few pointer hops, but that example I gave earlier, the set of 16 million items, you'll get a typical tree depth of about 4 or 5. It's a lot better than 24. And that's maximum tree depth. You may actually end up not going down the whole tree to get to your item. So maybe 3 or 4 hops on average. For 16 million items, it's not bad, I think. The nodes themselves, because you can limit the number of pointers you stick in there, you can still keep them cache friendly. So only 1 cache hit per node. So it's relatively cache friendly as well. And here's the best part. We're talking about persistent data structures. This is actually easier than the red-black tree to make persistent. First of all, because We don't have as many nodes to write back up to root, so we don't have as much of a cost there. And we don't have to rebalance, because the distribution is basically based on the distribution of the hash. You need a good hash algorithm. That's the one limitation. But assuming good distribution, it's effectively self-balanced. You never have to rebalance, so you don't have to pay that cost either. So this is like an almost ideal general purpose data structure to use, and is the default data structure in languages like Scala, I believe, and some others. So that's nice. And in fact, I'm going to be giving a talk at CPP now on my implementation of one of these, going into a bit more depth. So if you're there, come to that, and if not, the video will be out afterwards, I think. Just need to finish writing it now. All right, that's persistent data structures. I want to talk about one more data structure that you can think of as a container. It's an interesting container because it only contains up to a maximum of one item. So probably guess that I'm talking about optional, which will be standard optional in C++ 17. You can get it in Boost now, or you can roll your own. I've even got one in Catch. Actually, I made a bit of a slip up there recently. Was telling someone that you could take the version out of Catch and reuse it more general purpose, until somebody pointed out that, which I'd forgotten, I hadn't quite got the alignment right on the storage, but it's another story. So don't use that, but the Boost one should be fine. Okay, so what is optional? I'm sure you're familiar with it, but we're going to dig into some of the nuances of it. So just the basics. So it's something which represents a value or the absence of a value, without having to resort to sentinel values or conflating it with pointer semantics. But in use, it actually looks like we're using a pointer. We can do the true test to see whether it has a value, and then we have to dereference it to get the value out, or you can call it method. So what are we really getting out of it? I mean, we're being a bit more explicit in our intentions, so that's nice. And there is one method that helps us to be a bit safer, value or. And what this does is just allows you to coalesce the value, or if it doesn't have a value, a default value. So you either get whatever the integers in there, or this one. That's nice. It's a very common use case. Other languages have something like the coalescing operator to give you the same thing. But it's not really general enough. In particular, here it's an integer, it's fine, but imagine we had to go off and compute this value, and it was an expensive computation. We don't want to pay if we didn't actually need it, because we had the value in the optional. And we can easily solve that just with a helper function. So here's one I've written. It takes our optional and a lambda. I should have used forwarding references, but ignore that. And we just say, well, if we have a value, return that dereferenced. Otherwise, return the result according to our lambda. Simple. And now, well, basically the same example as before, but using the lambda. So we're not actually using that, but now we can do anything in here. We sort of open the door to lambdas and everything that can do. We can do expensive operations in there. So that's quite nice. It's a shame that the standard version doesn't have that. But that's passing in a lambda for when it doesn't have a value. We do it the other way around as well. So I've called this one with. You might see something similar with different names. So very similar, we take the optional and a lambda, but this time we only call the lambda if we have the value, and we pass the dereferenced optional on to it. So here's the usage. Say with this optional, if we have a value, so we've got the dereferenced value in here, it's very safe. We don't have to do the dereferencing ourselves, that's the unsafe bit. Now we're working with non-optionals. We do what we want. So that's nice, but there's an opportunity here. Think back to right at the beginning of the talk. We're talking about statements and expressions. We've given this statement semantics. It's a bit of a shame. The only thing we can do with that value is in here. But we can easily change that, make this an expression. Just have to give our if and else branch, and we need to return an optional. In this case, we're returning an optional of the same type. So again, if we have the optional, we call the lambda, but it must return the value now, and we'll return that. Otherwise, we return an empty optional. Now we can treat it as an expression. So if we have this integer, we'll do something with it, and we'll return the result of doing that. So what we've got over here is another optional int. So yeah, bit of progress, baby steps. We're getting somewhere. What else can we do with this? Well, it's a shame we have to return an optional of the same type. Can we change that? Of course we can. In fact, I've got a little bit of extra boilerplate up here. Sorry if it's not bright enough to read, but you don't have to worry too much about it anyway. It's just a little extra trait that says, well, if this type is already optional, then keep that. Otherwise, wrap it in an optional. So you can take any type and make it optional. So we say add optionality of the decal type of calling the lambda. So now we can, well, inside it's exactly the same. We either call the lambda or we return an empty optional. And now we can do type conversions. So here I'm converting the integer to a string. There's other ways to do it. Almost all of them more efficient, but serves the purpose. So that's nice as well. And still relatively simple. Okay. Well, there's another implication to this. Because with returns an optional, we can chain that to another call to with. So here's our inner call to with. We've got our inner lambda. We're multiplying by 2 here. We return that, pass it to the outer with, calls this lambda, and then we add 1 to it. So these only get executed if there's an optional, there's a value in the optional all the way down. And we end up with an optional on the outside. So we're composing our little snippets of algorithm now. That's quite nice. What I don't like about this is it's not very readable. You have to start from the center to work out what's going on and snake your way out. And I don't even know how to format this. It's just nothing you do seems quite right. And it's a shame that C++ just doesn't do functional composition very well. True functional programming language will have a way of effectively inverting this flow, give you a nice pipeline of algorithms that you can flow through. So you can't do that in a general way, C++. We could do it in this case. All we have to do is change our with function to an infix operator. In this case, I've chosen the bar operator, call it pipe, like Unix pipes. Nothing else has changed, but look what this does to the code. Much nicer, I think you'll agree. Now we can see exactly what's going on. Well, assuming you know what it's doing. So see the data coming in at the top, flows through, pops out the bottom. Sort of visually matches your internal representation. And it formats really nice and cleanly as well. And it scales. Let's add some more operations. I've got 4 here now, but you can just see all the code that's going on over here, nice and clean. So we've got our type conversion here as well, that's nice. This one's interesting. This is acting as a filter. So far, we only got an empty optional at the end if we put one in at the beginning. But now we're saying, well, if it doesn't meet some criteria, well, we're not even going to execute the subsequent steps. We're going to drop out. So we're composing these in very nice ways. And there's quite a few nice properties about this. Another one is, I mean, apart from this optional here for the filter, there's nothing about any of this that's specific to optional. Imagine that instead of optionals, we had, say, a vector of integers. Well, you could use something exactly the same, couldn't you? You just have a different helper operator. And it would just apply that whole sequence to every item in the vector and give you, in this case, a vector of strings out the end. It's a really nice property. It doesn't have to be containers. It could be some type of future. You could use this to do async. Fortunately, standard future as it is now. It doesn't quite work like that, but there's work afoot to make it work like that. You could do it with error handling. If you came to Niall's talk just before this, if you were sort of building up to something like this, you didn't quite get there. But yeah, you can use this to push all your error handling off to one side. So there's lots of things you can do with this. In fact, it's a really general, universal pattern that composes nicely. We have a name for it. It's called a monad. Brush some bits under the carpet. Like I said, I'm not going to go into some of the academic details. You certainly ask me afterwards, but this is a good example of a monad called the maybe monad. from Haskell. And if you want to see more examples, you should have a look at the ranges library, because large sections of ranges are monadic. Even the bits that aren't have most of the same characteristics anyway. So here's an example from one of Eric Niebler's slides in his CPP Con 2015 talk. If you haven't seen it, you must watch that. It's mind-bending in a good way. So here you can see it's using the same pipe character. And rather than inline lambdas, he's calling out to functions, but otherwise it's the same. And what he's doing here, if you haven't seen the talk, is he's trying to get this output, a calendar printed to standard out. Now think of the complexity involved in this sort of layout. Just think through from first principles. Well, don't think it through, just watch the talk, you'll see it. This is just his top-level driver code, composing all these nice, small, well-focused bits of functionality together. And just to give you an idea of how sort of nicely this is isolated, that, go back to the example. See, it's 3 months across. Well, that's just dictated by this chunk 3 here. Yeah? All these bits are pulled out, and you can change them independently. This is a really nice example. Watch the talk. And we carry on. I think it's a good point to bring up a quote from Kevin and Henny. This picture used with his permission. He did a talk on functional programming, and he had this to say. I meant to ask him whether he had the same thought in the evenings at the conference here. But that's a good point to start wrapping up, I think. So we started off talking about expression-oriented programming, why that was significant, what the implications are. We've sort of been discussing the implications of that through the rest of the talk. We went on to talk about immutability and how we get local reasoning from that, why that's important, and how to deal with immutability, a useful technique is builder types. And then type of builder type is, well, talked about strings, but then we talked about persistent data structures. And finally, we looked at some examples of monads. That's really all I've got to say here. Now, when I've done this talk before, it's been a 60-minute talk or less. Coming here, had a bit more time, and I was going to put some more material in on another subject of arithmetic data types. But then I heard that Vittorio Romeo was going to be talking about just that in his session before this. So I hope some of you at least went to that, and if not, should watch the video. That saves me giving a sort of a half-finished version of that instead. But in a way, the error handling monad that I mentioned is a form of arithmetic data type. And the way you can compose those monadically following all the same principles is sort of a really valuable way to do error handling. So it's interesting that previously Vittorio and Niall were on at the same time talking about very complementary techniques. But that's all I've got for now. I'm going to open up for questions. Actually, I finished a bit sooner than I expected. So thank you. Oh, by the way, all the references for all the things I've mentioned are on my site, this URL. So take a photo of that if you want. So yeah, that's it. Thank you.